Hello and welcome to Engineering Safari. Today's topic is DC and AC analysis of the bipolar junction transistor. So, this topic is actually a combination of various minor topics, and the concepts which have been learned earlier will all be put together into this topic. There will be a lot of circuits, a lot of different electronic materials, and the entire chapter is about how you can basically simplify a very complex circuit and find how the particular device works. So while it might look very tedious from the outside, I'll do my best to actually put it all in a very simple manner so that it's understandable for everyone. And the good thing about this subject is while it might be a little bit tedious at first and hard to get a hang, once you get a hang of it, it's a very easy subject. It's like all the derivations almost follow the similar steps. And once you get a hang of this chapter, the best thing is that the upcoming chapters are almost the same. So it's just the initial few bits which are a little tedious, and we'll do our best to get through them so that the entire subject is easy as a whole. So, first, let me just tell you what all we'll be covering in this particular lecture and in this particular module. So, the first thing that we'll be learning about is the bipolar junction transistor and what it is. So, that's just an introduction which most of us already know, and then we'll learn how a bipolar junction transistor behaves differently when it's biased with direct current and with alternating current. The DC part is a really minor chunk of this module, and it's really easy compared to the AC part. When it comes to AC analysis, we'll only be talking about small signal analysis. That is, when your input voltage is really small, and to be precise, the input voltage is lesser than your base emitter voltage. And since AC circuits tend to get a little complicated because of the presence of various capacitances in them, we use a model called the hybrid pi model, which is basically a combination of various circuit simplifying techniques. So using this hybrid pi model, we simplify our AC circuit so that we can analyze what the voltage gain actually is. And like I said, an AC circuit is pretty complicated because of the presence of various capacitances. So we'll also be learning in detail about what are the capacitances present in BJT and how they affect our analysis. After that, we'll learn about the Bode plot, what type of a graph we use for the Bode plot, and how it helps us to look at the voltage gain with respect to the frequency of the voltage that is actually being applied. And then we learn about how your how in AC analysis the voltage gain changes with respect to the frequency. It behaves differently for mid frequency, it behaves differently for a higher frequency, and the reason for this difference in behavior is the BJT capacitances, like I mentioned. So we learn in detail about how which capacitance is active at which frequency and how they tend to affect our voltage gain. And we'll conclude as to what is the best frequency for voltage amplification. And at the end, we have a small topic named multistage amplifiers, where we'll look at how we can make amplification even more optimal by adding multiple different BJTs. So what happens in a multi-stage amplifier is an input signal is sent into a particular BJT, and the output, the amplified output, is actually sent into another BJT. So this results in better amplification. So we look at how these multi-stage amplifiers can be used for better amplification. And at the end of this, obviously there will be some questions. Questions will be done both in the middle and at the end of each topic. So now let's get started with the topic. So like I said, the first thing that we'll be learning about is an introduction to the bipolar junction transistor. So basically there are two types of bipolar junction transistors. The first one is the NPN type and the second one is the PNP type. So in a BJT, there are actually two types of uh, like doped semiconductors at the ends, and in the middle we have a very thin portion which is differently doped. So in the case of an NPN BJT, we have N on one side, N on the other side, and a very thin p-doped region in the middle. So the N region on the left is called the emitter, and the one on the right is called the collector, and the thin region in the middle, which is differently doped, is called your base. So the basics of this is that your emitter is extremely heavily doped, your collector is mediumly doped, and your base is very lightly doped. So we do not really have to get into the physics of how this works. We'll explain that in different lectures later on when there is a necessity for it. But right now, this is all that is needed. The important thing for us here is that the behavior of this particular device changes based on how you bias each part of the transistor. So you can think of the transistor basically as two different PN junction diodes which are almost taped together. So in a PN junction diode, if your positive side is connected to the if your positive terminal is connected to the P side, we call it a forward bias. And if your positive terminal is connected to the N side, we call it reverse biased. So you can think of this particular transistor as two different PN junction diodes. So the one on your left is the emitter base configuration where your which should ideally be forward biased. So in this case, your positive terminal should be connected to the P side and your negative terminal to the N side. And in the collector based junction, we connect the positive negative terminal to the P side and the positive terminal to the N side. This is just the ideal case for amplification. And like I said, if you bias it differently, the device tends to behave differently. So in case both the emitter and collector based junction are forward biased, we have the saturation state. So here what happens is almost the entire current that flows from the emitter flows to the collector. So this is almost like a closed circuit where there is no current flowing anywhere else and no resistance is being offered. The second type of biasing that can be done is where both your emitter based and collector based junctions are reverse biased. So when there is a reverse bias, there is minimal and almost negligible flow of current, and this state is called your cutoff state where it behaves like a open switch. So the function of these two states is to act like a switch. So in the saturation state, your transistor behaves like it's a closed switch. And in the cutoff state, it behaves like it's an open switch. That is, there is no flow of current. So with a combination of these two, what we are looking at is a circuit which can be closed and opened just by changing the voltage which is applied to each part of the transistor. So these two in combination are basically used to serve the purpose of a switch. And the next case is when your emitter base is forward biased and your collector base is reverse biased. So this is the most important thing that we'll be looking at. So in this case, your BJT acts as a amplifier. So whatever voltage is input comes out amplified with the same frequency and other characteristics. So this is called your active state, and this is what we'll be looking at throughout the most of the chapter. The last one is pretty useless. It's when your emitter base is reverse biased and your collector base is forward biased. So this state is called your reverse active, and it's so useless that its function is in fact performance degradation. So this is not really important for us. The first three are what we'll be looking at throughout the rest of the chapter. So now let's just look at this device from the point of view of someone who is actually building the device, right? So like I mentioned before, for the transistor to work as an amplifier, it should lie in the active region. So we should we should select the device such that our device tends to almost always work in the active region. So the main thing for this is called your cue point or the operating point. For knowing exactly where the cue point should lie and what are the ideal characteristics for the BJT, we make a graph between the collector current and the collector emitter voltage. So the cue point should ideally lie exactly in the middle of this line. This line is called a load line, and the ideal placement for the operating point is exactly in the middle of this load line. So if this is the exact middle, this point will be VCE by 2 and this point will be IC by 2. IC max by 2 to be precise, and this is VCE max by 2. So we'll learn exactly what IC max and VCE max are a little later, but right now you need to know that the cue point should be exactly in the middle of the load line. What happens if the cue point is a little towards either side is, like you can see in this case, the cue point has gone a little too close to the y-axis. So whatever this input signal, some of it tends to go to the saturation region. So when the amplified output comes here, like you can see, the portion of this portion of the waveform is missing because amplification happens only in the active region. So the part of the signal that has gone to the saturation state has been missing from the output waveform. So waves are basically some sort of information that is being conveyed. So we can't afford to have parts of the wave lost, which is why we don't prefer this type of a operating point where parts of the signal get lost. Similarly, again, if the cue point goes too close to the x-axis, some portion of the input waveform goes to the cutoff state. And like you can see, again, some of the information tends to get lost because of this. So the ideal place for the cue point is exactly in the middle. So now what we'll do is we'll look at various designs of the transistor and we look at which one helps us to keep the cue point stable, and we look at what are the disadvantages with other designs of the BJT. So the first one that we'll be talking about is the fixed bias. So right now we are only talking about DC operation. So in DC, the first thing that you need to do is whenever you're talking about DC circuits, you need to open circuit all the capacitors. And the reason for this is we all know that the impedance of a capacitor is given by 1 by j omega c. And in a DC circuit, the angular frequency is basically 0. So 1 by 0 is giving us infinite impedance. So capacitors in DC offer infinite resistance to any current. So infinite resistance is similar to an open switch, due to which we just remove all the capacitors, we open circuit all of them. So what happens, you're fixed. So let's just pretend that these capacitors are opened and they don't exist. This is the only part of the circuit that we need to be looking at. So in fixed bias, you have the voltage source in the middle, and you have a base resistance to your left, which is directly connected to the base terminal, a collector resistance on your right, which is again directly connected to your collector terminal, and the important part here is that the emitter is grounded. So this is how the fixed bias circuit looks like. So now we need to find out what are the output characteristics of this particular configuration to know how optimal it is for us. So when we're talking about output characteristics for a BJT, we are always referring to IB and VC, which is your base current, the current flowing through this terminal, and the collector emitter voltage. That is the potential difference between these two terminals. So to find out these output characteristics, we'll be applying Kirchhoff's voltage law, but we'll not, like we used to do it in the conventional way, we'll not be applying it in the closed loop here. We'll be applying it at the boundaries. So the first place to apply this is the input side of the loop. So this region is the input side of the loop. So we'll go on applying KVL here. So KVL is basically the sum of all voltages in this loop will sum up to be 0. So like we can see here, the first thing is VCC, that is the voltage that we are supplying to the circuit. The second potential difference that we come across is IB into RB. And the last one is the potential difference between base and emitter, which is called VBE. So applying KVL, we get that VCC is equal to IB into RB plus VBE. So what we are looking to find here is IB, which is the base current. So from this equation, we can easily derive that IB is equal to VCC minus VBE divided by RB. So now to find out VCE, we look at the output side of the loop. And here again, we have only three things: VCC, your IC into RC, and the final collector emitter voltage. So using Kirchhoff's voltage law, we can again write VCC is equal to IC/RC plus VCE. And we can write VCE is equal to VCC minus IC into RC. And one thing is VBE is is a fixed value, but it depends on the type of the material that we use. For silicon, it's 0.7 volt, and for germanium, it's 0.3 volt. But silicon is what is usually used for making BJTs. So unless it's specified in the question, we are always going to assume that the value of VBE is 0.7 volt. Okay, so the next type of design that we're going to be looking at for a BJT is the emitter stabilized bias. So this is exactly the same as your fixed bias with just one minor difference. Like you can see, this part of the upper part of the circuit remains exactly the same. The only difference is that instead of the emitter terminal being connected to the ground, we have added a resistance with value RE, and the function of this is that it helps us stabilize the Q point. So we'll be looking at how that does, but before that, let's calculate the output characteristics for this particular design. So again, we apply KVL on the boundary. On the input side, we have VCC is equal to IB into RB plus VBE, and this time we have this additional potential drop across the resistor RE, which is signified by IE into RE. So clearly we can see VCC is equal to IB into RB plus VBE plus IE into RE. And the most basic thing in a transistor is the fact that the emitter current is equal to collector current plus base current, and your base current and collector current are related by a term called beta. So this beta is actually dependent on temperature, and this beta is what actually helps us stabilize the Q point. The knowledge of beta is what helps us stabilize Q point in this type of design. So we know that IE is equal to IC plus IB, and we also know that IC is equal to beta into IB. So because of that, we can write IE is equal to beta plus 1 into IB. We also have another variable called alpha, which is the collector current divided by emitter current, and these two variables, which these two constants, beta and alpha, are denoted by beta is equal to alpha divided by 1 minus alpha. So now to find out IB, let us apply KVL on the input side of the equation. So from that we'll get VCC is equal to IB into RB plus VBE plus IE into RE. And instead of IE, we can write that as beta plus 1 into IB, which will make it easier for us to get our base current out. So from this expression, we can find out what the value of base current is, which is VCC minus VBE divided by RB plus beta plus 1 into RE. So this beta plus 1 expression is what makes this design a better design than the previous one. Because what this does is it helps us stabilize the Q point. In fixed bias, like you can see, the value of IB does not depend on beta. So because of this, what happens is when your collector current goes on increasing, your beta goes on increasing. I mean, sorry, it's the other way. When there is an increase in temperature, the value of beta increases, due to which your collector current increases, but your base current remains the same. So because of this, what happens is your collector emitter voltage tends to fall back a lot. It tends to reduce a lot. So like I said, in the load line, the Q point should ideally remain exactly in the middle. So now if the value of collector emitter voltage decreases, what happens is the Q point tends to move towards the y-axis, due to which we do not get optimal amplification. So this was the main drawback with our first design, which was the fixed bias circuit, due to which we stabilized it by adding a resistor to the emitter instead of directly grounding it. So what this has done is it has made our base current dependent on beta. So now whenever beta increases, our base current increases too, due to which the Q point tends to remain at the same spot. So the third type of configuration that we're going to be looking at is called the collector to base configuration. So here what happens is the supply voltage is directly connected to the collector resistor RC, and the current splits after passing through this resistor. So all this while, the current passing through this resistor and the current flowing through the actual collector terminal into the transistor were the same. But now what happens is the current is splitting at this point. Some of this current goes through the base resistor while some of it flows into the transistor, due to which we have to label these two as using different variables. We use IC dash over here and IC over here. So now let's apply KVL on the input side. We get VCC is equal to IC dash into RC. The current flowing through this resistor is not IC, it's IC dash, plus IB into RB, plus the voltage VBE over here, plus IE into RE. So even though IC dash and IC are not exactly the same, we almost always tend to assume that your base current is a very small quantity, due to which we are assuming that IC dash, IC and IE are almost the same. Just for the simplification of our calculation, we take these assumptions, which help us get a decently approximate value. So because of this, we can take IE is equal to IC is equal to beta into IB. So we replace IC dash with IB into beta. We replace IE with beta, and we replace IE as well with beta into IB. So because of this, we get our expression for beta as VCC minus VBE divided by RB plus beta into RC plus RE. Like you can see, again the value of base current depends on beta. So whenever the value of base current tends to depend on this beta, we can get an assurance that it's comparatively stable. The Q point is comparatively stable. So now applying KVL on the output side, we get BCC is equal to IC dash into RC plus VCE plus IE into RE, right? So we can write, we have already made this assumption that IC dash, IE and IC are almost the same. So we can replace IC dash and IE with IC. So because of this, we get a very simple expression for the collector emitter voltage, which is VCC minus IC into RC plus RE. So the last type of configuration that we'll be looking at is the voltage divider bias. So here things get a little complicated for us because, as you can see, there are a lot of resistors here, and the first thing that we'll have to do is simplify them so that our analysis becomes easier. So for that, what we do is we use Thevenin's theorem to reduce these two resistors down to one. So like you can see, VCC is the supply voltage and these two circuits are connected in parallel. So the first thing we do is we actually take VCC as two different inputs. This is my R1 and this is my R2 and this is my transistor. This is again my supply voltage VCC. This is my resistor, the collector resistor, and this is grounded and this is grounded. So because these two circuits were connected in parallel, we can take the we can assume that the source voltage is being assumed on each of them independently. So like you can see, this is our source voltage and this terminal, the R2 resistor is connected to the ground. So what we do, because of that, we can join this terminal here and it will behave like a battery where this is the higher potential and the ground is the negative terminal or lower potential. So now that we have a simplified circuit like this on the input side, we replace it with a different voltage, different value of a voltage and the different value of a resistor. So what Thevenin's theorem says is that any complex circuit can be reduced to a simple circuit where there is just one potential source and one resistor. So we find the resistor by short circuiting. We find the equivalent value of RTH by short circuiting this. So when we short circuit this, we get R1 is parallel to R2. So that is what our equivalent resistance will be. And to find to find VTH, what we do is we actually remove the voltage source and calculate what the potential difference is across this particular terminal. So you can see that the resistor R2 is in parallel to this particular potential source. So the easiest way to calculate VTH for all of these simple circuits is just look at the resistor which is connected in parallel with your potential source and calculate what the voltage across that particular resistor is. That will give you the value of VTH. So using the voltage divider rule, we know that the potential across R2 will be VCC into R2 divided by R2 plus R1. So the potential across R2 what will act as my Thevenin's voltage, and my RTH will be R1 is parallel to R2. So now by simplifying the input side, now we have a much simpler circuit. This is my RTH and this is my VTH, and we just derived the value of RTH and VTH. So now let's apply KVL and find what the output characteristics are. So this applying KVL on the input side, we get VCC is equal to IC into RC plus IB into RB plus VTH, right? So now we can replace I. Wait, oh no, sorry. I'm very sorry for the confusion. Here we actually apply KVL in the closed loop here. So the closed loop here is what actually acts as our input. So because of that, we apply KVL in this closed loop. So here what we get is BTH is equal to IB into RB plus VBE plus IE into RE. So like we know, our emitter current is given by beta plus 1 into base current. So we can replace our IE with beta plus 1 into IB. Because of this, we can finally get the expression for IB. Now applying KVL on the output side, we get VCC is equal to IC into RC plus VCE plus IE into RE. Now we can assume that IC is almost equal to IE, due to which we can replace IE with IC, and we get VCE as VCC minus IC into RC plus RE. Now there is a small trick that helps us solve questions, which is called the thumb rule. So this is used when they give you a circuit like this, but do not give the value of either R1 or R2. So through this, we can approximately say that the amount of current that is flowing through R2 is 10 into IB, and the amount that is flowing through R1 is 11 into IB. So like you can see, the direction of current tells us that 11 into IB comes here, 1 into IB, that is your base current, goes here, while 10 into IB tends to flow straight through the resistor R2. So this is a approximation that is used to help us solve questions. This is only supposed to be used when neither R1 nor R2 are given in the question. So the the main point of all of this was to find the Q point such that it lies exactly in the middle of the load line. So most of our questions will be related to actually drawing the load line and plotting the Q point on it. So we need to know both the x-intercept and the y-intercept of the load line, and also find out where the Q point lies. So the Q point lies exactly in the middle of the load line. The y-intercept of the load line is where your IC is maximum, like you can see. And since it's cutting the y-axis, it means whatever your whatever your x-axis is, I mean your x coordinates, that is equal to 0. So when your collector current is maximum, your VCE is equal to 0. And at this point, collector current is given by the formula VCC by RC plus RE. So this is the maximum value of collector current. And at your x intercept, where the value of IC becomes 0, this is where the value of your VCE becomes maximum. So at this point, your VCE is directly equal to VCC. So basically what happens here is, since your VCE becomes equal to VCC, there is no potential difference across this particular terminal, due to which there is no current flow here. And if the current flow is maximum, that clearly means that the potential difference is high. So the potential at the other end has to be quite low in comparison. So when your IC is maximum, your VCE is minimum, and when your VCE is maximum, your IC is minimum. So the coordinates of the Q point are always IC max by 2 and VCE max by 2 because it lies exactly in the middle of the load line. So now we have some questions. So let's see how we can solve this. So by looking at the question, the first thing you have to do is identify what type of configuration this is. So we can understand that this is a voltage divider bias. And since we are talking about DC biasing, the first thing we'll do is we open circuit both the capacitors, all three of the capacitors. So they basically have no role. Our circuit looks like this now. This is grounded and this point is connected to the transistor. So since this is our voltage divider bias, the first thing that we have to do is simplify the input side by using Thevenin's theorem. So to find RTH, like we already discussed, RTH is R1 parallel to R2 and the value of R1 here is 10 kilo ohms and R2 is 5 kilo ohms. So R1 parallel to R2 is R1 into R2 divided by R1 plus R2. And R1, we have the value of R1 as 10 into 10 to the power 3 plus, and R2 is 5 into 10 to the power 3 divided by, this is a multiplication, and this is divided by 10 plus 5 into 10 to the power 3. So this 10 to the power 3, 10 to the power 3 get cancelled and we are left with 50 divided by 15 into 10 to the power 3. So we can write this as 3.33 into 10 to the power 3 ohms or 3.33 kilo ohms. And after finding RTH, the next thing we need to find is VTH, which is given by R2 into VCC divided by R1 plus R2. So the value of R2 here is 10 into 10 to the power 3. The value of VCC is 10 and R1 plus R2 is given by 15 into 10 to the power 3. So the 10 to the power 3 get cut and we are left with 100 by no, so we are left with uh, where did I go? Sorry, the value of R2 is not 10, it's 5. So we have 50 by 15, which gives us 3.3 volts. So now we have VTH and RTH. So, so the output characteristics that we are looking to find are IB, VCE, and we need to find the value of IC as well to plot our load line. So let's start with IB. So for IB, the formula was VTH minus VBE divided by RB plus beta plus 1 into RE. For now, while solving the questions, we can just look at the formulae or keep a formula sheet separately so that it helps us to just get a hang of the concept and how to approach a problem. And as we solve a few problems, the formulae get ingrained in our brain easily. But make sure that before the exams, the formulae are learned. For now, it's okay to just have a look at the formulae and solve them. So we know that IB is equal to VTH minus VBE divided by RB plus beta plus 1 into RE. So the value of VTH here, like we found out, was 3.33 volt and like I said, VBE is always fixed at 0.7 volt unless it's mentioned in the question. And the next thing that we have to substitute here is the value of RB and the value of beta plus 1 and the value of RE. So RB is RB is basically RTH, which we found out to be 3.33 kilo ohm, and RE is 500 ohm. So we have 3.33 into 10 to the power 3 plus beta plus 1 into RE. Alright. So I think this question has forgotten to give us the value of beta. So let's just take the value of beta to be 100. This should have been given in the question, and ideally it will always be given in the question. But since it's not been given, let's just take a value which is easier for our calculation. So now we have 2.63 divided by this will become 101, and we know that the value of RE is 500. So we have 3.33 into 10 to the power 3 plus 101 into 500, which gives us 50.5 into 10 to the power 3. So upon simplifying this, we get 2.63 divided by 3.33 plus 50.5, which is 53.83 into 10 to the power minus 6. So upon simplifying this, we get 10 to the power minus 3. So upon simplifying this completely, we get 48.86 into 10 to the power minus 6 ampere, or 48.86 into 46.86 microampere. So this is the value of our base current, and we know that collector current is equal to beta into base current, and we have that the value of beta is, we are given that the value of beta is 100. So 100 into 48.86 into 10 to the power minus 6. So that gives us 4.886 into 10 to the power minus 3 ampere, or 4.886 milliampere. So this is our value of IC. So now for calculating the value of IE, IE is equal to IC plus IB. So by adding these two, we get a value which is very close to IC, but it's not exactly the same. So we get 4.935 milliamperes. So now we have found out the value of collector current, base current, and emitter current. So this particular value of collector current that we have obtained, this is the value of collector current at Q point. This is not the point at which it intersects the x-axis. This is the value of, I mean the y-axis. This is not the maximum value. This is the Q point value of IC. Similarly, when we use KVL and find on the outer loop and find the value of VCE, the value we get will be the Q point value. The intercept values are found out by using these two formulae alone. VCE is equal to VCC and IC is equal to VCC by RC plus RE. So to find the Q point values of these particular characteristics, we use KVL, and to find out the intercepts, we use these two formulae. So now I have to apply KVL on the outer loop over here to find the value of VCE. So VCE is given by VCC minus ICRC minus IE into RE. So in this case, we know that VCC is 10, IC is, we found out IC to be 4.886 into 10 to the power minus 3. My RC is 1 into 10 to the power 3. IE was found out to be 4.935 and the value of RE is 500 ohm. So this is 10 to the power minus 3 and this is 0.5 into 10 to the power 3. So we get 10 minus the the 4.886 minus 4.935. So this value comes out to be 2.36 volt. No, this is not 4.935. This is 4.935 by 2, which comes out to be 2.46. So the final result comes out to be 2.36 volt. So now we know VCE at Q point. We know the value of IC at Q point. So we need to plot the load line and the Q point now. So this is my VCE and this is IC. So the intercept is when VCE is equal to VCC. And VCC here was 10 volt. So it intersects this axis at 10. And the Y intercept is given by IC max is equal to VCC divided by RC plus RE, and VCC is 10 volt, RC is 1 kilo 1 into 10 to the power 3, and RE is given by 0.5 into 10 to the power 3. So this gives me 6.67 into 10 to the power minus 3 ampere, which is 6.67 milliampere. So this intercept is 6.67 and the value of Q point is VCE is 2.36 and IC is 4.886. So this is how we draw the load line for this particular expression. So this is a question that you can just try on your own. The hint here is that you will have to use the thumb rule to find out exactly how much current goes through R1 and R2 because both of them are variables in this case. So with that, we come to an end of the DC analysis part. So the next topic is small signal AC analysis. So like I said, the main difference between AC and DC analysis is in AC analysis we could just ignore the capacitors and open circuit them. But in DC analysis there are a lot of additional capacitors and the inbuilt capacitors which are always present in the BJT, they all come into play. So depending on what frequency you supply, the frequency of this source voltage, certain capacitances come into play and they affect the circuit in different ways. So the most important factor here is that we'll only be looking at small signal analysis. So your input voltage has to be lesser than VBE. So the reason that we are only taking small signal is that we are going to ensure that the BJT remains in active region always. So like unlike the load line that we were plotting in DC analysis where we had to ensure the Q point stays in the middle, we are already taking a very small voltage. So wait, let me just go to the Q point graph to show you what this means. Yes. So see here the input signal tends to go outside into the saturation and cutoff region when Q point is not placed ideally. However, since we are just taking a very small signal, the magnitude is small. If this was the case, if this was our input signal, it wouldn't really matter if the Q point moved a little bit. So we are only going to be looking at small signal analysis where we don't have to work on stabilization of the Q point. So in alternating current, unless it's a specific case, the capacitors are usually short circuited because, like I said while I was explaining for direct current, the impedance is given by 1 divided by j omega c, and these capacitances have a large value. So if my omega is 0, it really doesn't matter about how large the capacitance is because your impedance just turns out to be 0. I mean, the denominator turns out to be 0 and the impedance turns out to be infinity. So because of that, we could just open circuit them. But now what happens is, if your omega is a non-zero value, the capacitor which is in the denominator tends to make it such that the impedance is very small. So let's say we have a capacitor which is in the 10 to the power 15. On so on going to the numerator, it becomes 10 to the power minus 15. So this signifies that the impedance is very very small. So a small impedance basically means that there is no resistance being offered. So that is behaving almost like a straight wire. So in case of alternating current, capacitors are short circuited, and in case of direct current, they are open circuited. So, so the first step in our AC analysis will always be to short circuit all the DC sources. The second step is to short circuit all the capacitors unless mentioned, and I mean unless the case is a very specific one and the capacitors are such that they will affect the circuit, we need to short the capacitors, and then we use various network theorems and techniques available to simplify the circuit. Like we use Thevenin's theorem, we tend to use two-port networks and other network theorems to simplify this. So these are the three basic steps for AC analysis. So now let's have a look at the basic. These are the basics that you need to know before we start AC analysis because they are essential to actually understand the concept. So the first thing is, what is a two-port network? So before that, let's have a look at the components that we already know, like a resistor, an inductor, and a capacitor. These are all one-port networks that have two terminals. So if this is your resistor, it has one terminal where the current enters and one terminal where the current leaves. So this is a one port network. On the other hand, devices like transistors, transformers, and operational amplifiers, these have four different terminals, and the the particular device is at the center. So current flows, there is an input current from this side and there is an input current from this side as well. And then the current flows in this direction here and here. So due to this, there is a potential difference which is being created on both sides of the device. So this is what a two-port network basically is. And we don't need to go, like I said again, this is a module which is dependent on the basics of various other chapters. So we'll just have a look at the basics and not go too much in depth about what these actually mean. So this is what a two-port network looks like. And in a two-port network, one side of the voltage and the other side of the current are dependent quantities. And the other two quantities are independent. So here V2 and I1, let's assume they are the independent quantities, and your V1 and I2 depend on these two quantities. So like I said, V1 and I2 are dependent on I1 and V2. So let's say your V1 is a function of I1 and V2 F1, and your I2 is a function of I1 and V2 F2. So if any variable is a function of two other variables, we can write it in this form. dv1 is equal to dou v1 by dou I1 into di1. And since it's also dependent on dou v2, we write the same thing with dou v2 and dv2. So like you can see here, we label all of these partial derivatives with h. So this h signifies a hybrid parameter. So hybrid parameters basically they mean different, they stand for different things at different places. So here like you can see this hi, it means impedance because it's voltage divided by current, which is impedance. Your HR is reverse voltage gain because it's the output voltage divided by input voltage. Sorry, it's the input voltage divided by output voltage, which is why it's the reverse voltage gain. And HF is forward current gain because I2 is the output current and I1 is the input current. And the final one, I2 by V2 is HO, and this HO basically means admittance because current by voltage is the reverse of impedance, which is admittance. So these hybrid parameters denote different values at different points. So like I said, we now that we have dv1 is equal to hi1 into di1, we can just integrate both the sides and get our simplified expression as v1 is equal to hi into i1 plus hr into v2, and i2 is hf into i1 plus ho into v2. So now that usually what we do in circuits is we are given a circuit, we apply KVL on that, and we get this equation, right? So now we'll basically be reverse engineering the process. We are given an equation and we are going to try and draw the circuit for it. So now what we do is on the first equation we apply Kirchhoff's voltage law. So the first thing that we have is there is a potential difference V1, and then we have a potential drop of HY in HI into I1. So if there is a potential, like I said, HI means an impedance because it's the value of voltage divided by current, and there is a current I1 flowing through it. So the potential drop across this particular impedance is HI into I1. Then we have a voltage source. The third potential difference that we'll be looking at is dependent on a completely different potential source V2. So when we have a voltage which is dependent on some other voltage, we can use a dependent source. So this is a voltage dependent voltage source, and we can signify it by HR into V2. So with this, we have one side of our circuit, one side of the two-port network done. So to find out the other side, we'll apply KVL on the second equation. So applying KVL on the second equation, we have I2 is equal to HFI1 plus HOV2. So here what happens is the current I2 flows here and it splits into HO and HFI2. HFI1. So the current I2 is obviously a sum of the current flowing in both the branches, right? So HO, like we know, is admittance. So HO into V2 will obviously give us the current, because this is current divided by voltage, and we are multiplying it with a voltage. So that will give us a certain current I. It's not the entire current I2, because the entire current I2 will be a sum of both of these. So we have a admittance. This is not exactly a resistance, because this is something that we are using to denote admittance. So the part of the current which is dependent on V2 comes from here, and the part of the current which is dependent on I1 is denoted by a current dependent current source, which is denoted by this diamond shaped arrow. So I2 basically comprises of both of these currents. One of these currents is dependent on I1 and the other one on V2. So this is how we draw the circuit on our output side. So we have the left hand side of the circuit here, and we have the right hand side of the circuit here. Now let's put it together and see how it actually applies for a BJT. So we have a base here. So since we are talking, we'll only be talking about common emitter, right? So the emitter is common to both the input and the output. So we have an emitter on both ends here. We attach a base to the input. Our base is the input side and our collector is the output side. So the potential difference V2 is VCE and the potential difference V1 is VBE. And let's replace, uh, I mean, not exactly replace, let's denote HR and HO, HO here with the E terms, HOE and HRE. So this is how your transistor actually looks when you look at it from the point of view of a two-port network. So one thing that we do is when we are choosing materials, we take them such that these two values are actually not very relevant for us. That is, we just choose a circuit design and material such that the quantities which are actually dependent on the emitter can be removed from here. So this particular voltage source and this particular resistor will both be removed. So the final hybrid model that we have is one resistor here and a current dependent current source on the other side. So this resistor is denoted by R pi, and this current dependent current source is denoted by a value Gm into V pi. So V pi is the potential difference across R pi, and it's also equal to VBE. And we can write R pi as beta plus 1 into RE because of this particular rule called the resistance reflection rule. So what this resistance reflection rule says is that if you have anything in a emitter branch, let's say you have a resistor, capacitor, it doesn't matter. You can remove it from the emitter branch and place it on the base branch by replacing it with, I mean, not replacing it. You can put it in the base branch and change the value to beta plus 1 into whatever the value was in the emitter branch. So let's say we had a resistor in the emitter branch of value R. You can, it's equivalent to there being no resistor in the emitter branch and there being a resistor in the base branch of beta plus 1 into R. I mean, a resistor of the value of beta plus 1 into R ohms. So because of that, we can say R pi, which lies in the base branch, is equal to beta plus 1 into RE. So this GM that we have here is actually uh, a term for term called transconductance, and it's denoted by beta by r pi, and it's also denoted by IC divided by VT. So IC is the collector current and VT is thermal voltage. And thermal voltage, like the name suggests, varies based on the room temperature. I mean, varies based on the temperature, but at room temperature, the fixed value for VT is 0.026 volt or 26 millivolt. So again, unless it's specified in the question that it's operating at a different temperature, we assume that this is the particular value of thermal voltage. Okay, so that basically tells us, that basically covers up the hybrid model part. So that covers up the hybrid model part, and next we'll be looking at the various types of capacitances which are present in a AC circuit, due to which our analysis becomes different from the DC one. So there are three basic capacitors like I showed: CC1, CC2, and C3. So your CC1 and CC2 are called coupling capacitors, and the C3 is called a bypass capacitor because it bypasses the current flowing to the emitter through the emitter resistor. So apart from these three capacitors, there are also inbuilt capacitors between terminals of the BJT. So since this is our bipolar junction transistor, this is our emitter, this is the base, and this is the collector. So like I said at the start, this behaves very similar to two different PN junction diodes, and we know that there is a depletion region in between both of them. And whenever you have a depletion region in a PN junction diode, there is always a certain capacitance that is formed across the depletion region. So because of that, you have a certain capacitance between your base and emitter terminals, and a certain capacitance between the collector and base terminals. So we denote them with certain names. The capacitance between the emitter and base is called C pi, and the capacitance between the collector and base is called C mu. So C pi is given in more detail by your the capacitance in the depletion region plus the junction capacitance, and your junction capacitance is usually denoted by 2 into Cj E naught. So Cj E naught is basically the value of junction capacitance when there is no voltage supplied to the particular BJT. Upon supplying a voltage, the junction capacitance changes and it becomes CJE. So this is just an approximation that we are taking, that CJE is equal to, almost equal to 2 into CJE naught. And so we can see that the emitter based capacitance, which is C pi, is is actually a sum of two different capacitors which are in parallel, which is your depletion region capacitance and the junction capacitance. So the thing is, we have seen five different capacitances so far, and these capacitances are a nuisance to anyone building a device, which is why they've been named parasitic capacitances. So what they actually do is they reduce the amplification, they reduce the voltage gain which we actually get, and so like I said, these capacitors don't always actually act. In most of the situations they are short circuited, but in the situations where they act, they really reduce the amplification of the device. So this is the graph which tells us at what frequency what capacitors are actually active. So if your frequency is low, the coupling and bypass capacitors, coupling capacitors are CC1 and CC2, and the bypass capacitor CE. These three capacitors become active, due to which your voltage gain becomes lesser and lesser as the frequency becomes less. And at high frequency, your inbuilt or parasitic capacitances, which are C pi and C mu, these tend to become active, due to which, again, as you increase the frequency beyond a certain limit, the voltage gain tends to fall off. So the region in the middle, which is called the midband, where the frequency is not too high or not too low, this is the ideal region for amplification. So this graph is always plotted on a semi-log sheet and not a normal sheet, because the y-axis varies normally. At equal units, there are equal intervals. However, the x-axis varies exponentially. So if you have 10 here, you have 100 here, and 1000 here, and so on. It varies exponentially because we are trying to fit a large range of signals into this graph. So this is plotted on a sheet where one side is a logarithmic sheet and the other side is a normal graph. So that is about what this graph means. So we know that the midband or the medium frequency range is actually optimal for voltage gain. So now we'll look at the different frequencies and the different behavior of this device at higher and lower, and how it's actually affected at each place. Yes, finally, the handwriting was really horrible till now, and I know I'm very sorry for that. Which is why I resorted to just writing it on a notebook and putting it up. I really hope this is better. So the first thing we'll talk about is the cutoff or transit frequency. So like you can see, the circuit over here has a lot of differences to the circuit that we actually came up with. So the reason for that is we add a lot of resistors between terminals, and what these resistors actually do is, excuse me, they stop abrupt flow of current to the transistor. If we directly connect a voltage source to the transistor, we always risk damaging it. So because of that, we add a few resistors in between so that the current from the voltage source does not flow straight into the device and damage it. So because of that, we have a few additional resistors, which is R pi here and R naught. And in a two-port device, we always add the voltage source on one side and short circuit the other side. Or we add a current source and open circuit the other side. But like I said, this is not very important. This is what we'll be doing here. So we attach a voltage source on one side and short circuit the other side. And like we discussed when it came to the capacitances, the part between collector and base, we have a capacitance which is termed as C mu. So this is the part between collector and base junctions. So we'll have a capacitor C mu here. And the part between your emitter and between the base and emitter, you have a capacitor which is C pi. So this is where C pi lies. It's between the base and emitter terminals. Okay, so now let's try and obtain the characteristics of this. We can remove this particular resistor because of the short circuit that is connected in parallel. So we have a point C here. So let's apply KCL here. So the current, we can see that current flows in three different directions at this point. So our KCL equation is minus IC plus GM into V pi, and the current flowing towards the left is, like we can see, the potential difference across the C pi resistor is V pi, right? Because The potential difference across R pi is V pi, and since C pi is in parallel, the same potential difference exists across the capacitor as well. So we have minus G pi plus Gm into V pi, uh, and here the potential difference across this is actually minus V pi, and the impedance in this particular case is 1 divided by j omega into c mu. So we always replace j omega with s throughout this module to keep things simple. So we can write v pi divided by 1 divided by s into c mu. So is equal to 0. So we can write IC is equal to gm into v pi minus v pi divided by 1 by s into c mu. So this c mu s into c mu goes on top. So we have g pi gm into v pi minus s c mu v pi. So taking v pi common from this, we can write our collector current is equal to v pi into gm minus s into c mu. Right. From this we can find our collector current. So now to find base current, we apply KCL on the other node here, which is P dash. So applying KCL here, again there are currents flowing in three directions here. So one direction is your the downward direction is V pi by R pi. The rightward one gives us V pi divided by 1 by S C mu, and the third direction gives us, that is the one flowing through the capacitor, that gives me V pi divided by S C mu. So there aren't three, actually there are four currents flowing here. One is, let me just erase this is a mess. So the four currents flowing from B are the one here, the one downwards, the one through the capacitor, and the one flowing straight through C mu. So since there are no devices between these 2 points, we can overlap them and consider them as a single node. So we can write, so after applying KCL here, we can write IB is equal to V pi divided by R pi. So R pi is the downward current, IB is the current from the left, V pi divided by 1 by SC mu is the rightmost current, and the other capacitor gives us V pi divided by 1 into V pi divided by 1 by SC C pi. So we have written the KCL equation for the other node as well. So again we take V pi common here, and we have 1 by C pi plus S into C pi plus S into C mu. This is R pi, just in case my handwriting is terrible. So now we are looking at current gain. So current gain is the collector current divided by base current, because your collector current is the output and base current is the input. So looking at current gain, now we substitute the values of IC and IB that we obtained, and we get V pi. V pi is common in both of them, so we can just cancel it out. We are left with Gm minus SC mu divided by 1 by R pi plus SC pi plus SC mu. So again we take R pi as, we just multiply both of them with R pi, the numerator and the denominator, and this is what we're left with. So one more thing is, like I said, the capacitance here, which is C mu, is a very small quantity. C mu and C pi both are very small, because the devices are always built in such a way that these parasitic capacitances are minimum. But However, we can't completely eliminate them because of which we have to perform analysis to understand how they behave at high frequencies. However, because these are very small, we can neglect them in these equations. So since Gm is much larger than Sc mu, we can just neglect this part of the equation and write it as Gm r pi divided by 1 plus S into C mu plus C pi into R pi. So we know that Gm into R pi gives us B. We know that Gm is equal to beta divided by R pi. So we can write Gm into R pi as beta. And we write it as beta naught to signify a very specific beta naught that is only for low frequencies. So after we replace our GMR pi with beta naught, we are left with beta naught with this equation, and we know that omega is equal to 2 pi into f. So we replace omega with 2 pi f, and then we take 2 pi and the rest of the expression common, leaving only j and f. So this expression that we got here, which is 2 pi c pi plus c mu into r pi, this equation here, this is denoted by f beta, which tells us that this is the beta cutoff frequency. So we can replace this with 1 by beta, f beta, and we are left with beta naught divided by 1 plus j into f by f beta. So this tells us how much the current gain actually is, and to get unity gain frequency, we have to take a very particular value of the frequency so that we get unity gain, which is where the current gain is 1. So for current gain to be 1, this entire expression has to be equal to 1. So we get beta naught by 1 plus, it's not just the expression which is 1, it's actually the magnitude of the expression. So we have magnitude of beta naught divided by 1 plus jft by f beta is equal to 1. So upon finding the magnitude, when you have any complex number of a plus bj type, the magnitude is always root under a square plus b square. So here the b is ft by f beta and a is 1. So we have root under 1 square plus ft by f beta square. So we just transport this there, and since ft and f beta are comparatively high values, we neglect 1 here and we are left with ft by f beta is equal to beta naught. So ft is equal to beta naught into f beta. So this is called unity gain bandwidth. That is, at this particular value of frequency, the current gain that you are getting will exactly be 1. So that is about unity gain frequency, and we already have covered most of this. We have covered the formulae for GM, R pi. Yeah, okay, that's nothing. Okay, so the next topic that we are going to be covering is the high frequency response. So the important thing here is, in high frequency response, the parasitic capacitances or the inbuilt capacitances, which are C pi and C mu, they are active, and the other capacitances like CC1, CC2 and CE, they're all short circuited. So this is how a high frequency response circuit looks like. We usually have the R pi and GM V pi alone, but since Since it's a high frequency response and these capacitors are active, we have to attach those capacitors, and we have resistors between every terminal to ensure that to avoid abrupt flow of current to the transistor. So unfortunately, you will have to actually memorize this, though it's not hard because you just know that you have to join a few capacitors at these terminals and a resistor between every terminal after that. You have RO, which is the output resistance, RC, which is our collector resistance, and RL, which is the load resistance. The load resistance is directly, it's directly related to the output voltage. You just have to find out the current flowing through the load resistance, and that will give you the output voltage. So, since we have a really complicated circuit, what we have to do is we use our networks theorem to try and simplify this circuit. Even though this is actually a simplified circuit in comparison with the original ones, because we have used the hybrid pi model and simplified it, it can still get further simplification. So the first thing we do is we look at the input side and see how we can simplify it. So this circuit can be simplified using Thevenin's theorem. So first we simplify only the leftmost portion of it. So here if we have to look at what is the what is if we open the voltage source, what is the potential across it. So we have a look at what resistor is in parallel to the voltage source, which is RB. So we have to find the potential difference across RB. That will give us our VTH. So VTH will clearly be using our voltage divider rule. We know that potential difference across RB is V signal into RB divided by RB plus R signal. So this will be my VTH, and RTH will be if you short circuit this, these two end up being in parallel to each other. So RTH is R signal parallel to RB. So now we have simplified that and we got this expression. Now we again apply Thevenin's in this circuit to simplify it even more. So here what we have is R pi is the resistor which is in parallel to the supply voltage. So the voltage across these terminals will be the potential difference across this. So that is the potential difference across R pi will be VTH into R pi divided by R pi plus RTH plus Rx. So, and we know that VTH is V signal into RB plus divided by RB plus R signal. And we also know RTH is RB parallel to R signal. So we replace these by all of that. And the final R Thevenin is when we short circuit this, what happens? RTH1 and RX are in series and their resultant is in parallel with R pi. So we have RTH1 plus RX in series and that is in parallel with R pi. And we know RTH again is RB in parallel with R signal. So we have simplified this complex circuit here into a relatively simpler one with just one voltage source and one resistor. And we know the value of that potential, the voltage source is this, and the value of the resistance is this expression. So on the right hand side, the output side, we have three resistors, all of which are in parallel. So that's very easy to calculate the equivalent resistance. It's just R0 parallel with RC, parallel with RL. So now we have simplified the circuit a lot in comparison to what it was earlier, but we can simplify it even further. So what we do is at point C we apply KCL. So on applying KCL, we can see that the current is going in three directions. Here we have IC, here we have GM and here we have the current flowing through C mu, the capacitor. We can take that as I mu. So we have this expression, which is IL is equal to wait, this is not IC, this is IL, because that is the current flowing through our load resistance. So we have IL is equal to GM into V pi minus I mu. So we know that the current flowing through the capacitor is very small, because the value of the capacitor itself is really small, due to which they have high impedance. So when you have a capacitor here and you have this GM V pi here, almost all the current coming from here is going to flow through here, because there is a very high impedance across this capacitor. So due to which we are going to neglect the amount of current that flows through the capacitor and instead directly write IL is equal to GM V pi. So after we write that, we know that the output voltage is the potential difference across the collector and emitter, because when we initially solved two-port networks itself, the first thing that we decided was that this is the collector terminal and this is the emitter terminal, and this is our base and emitter terminal. So this is the base emitter is what is the input and the collector emitter is the output. So my VCE is what my V output is. So now we know what IL is. Let's try and find what the voltage gain in this place actually is. So I have VO is equal to minus GM into V pi, and no, this is IL, and IL into RL dash is what gives me VO. So upon taking V pi here, I get VO by V pi is equal to minus GM RL dash. So our voltage VO was the output voltage. We are supposed we are supposed to try and find a relation between the output voltage and the input voltage that we got here, which was V signal. So our main aim is to find a relation between VO and V signal, and we already have V signal in terms of V pi. So what we are going to do is express V signal in terms of V pi, and we already have VO in terms of V pi. So by using V pi in common between both of them, we're going to try and find the expression between V signal and V output. So now we used an approximation that there is no current through I mu and solved the expression for V output. However, now we know that there is a very tiny current flowing through. So to find that current, we can actually use V pi minus VO, which is the potential difference across here. This is VO and this is V pi. So VO minus V pi minus VO, and the impedance between is that of capacitor C mu. So I have I mu is equal to j omega into C mu into V pi minus VO, and I can write VO as minus GM RL dash into V pi, like I just saw here. VO is equal to minus VO by V pi is equal to minus GM RL dash. So upon taking V pi common here, I will get 1 plus GM RL dash. So now the last thing that we have simplified the rest of the circuit quite a bit. The last thing that we will do is we will try to express the circuit with just one capacitor and not two. So for that, what we do is these two capacitors are not in parallel. What we are going to try and find a capacitance C equivalent, which will give us a circuit which is equivalent to this. So we find a capacitor of certain value that upon attaching that capacitor and removing C mu, our circuit will not change at all. So to find the value of this particular capacitor C mu, I I take a look at this I mu, and so we know that I mu is equal to this, the current flowing through this C mu and then directly through C pi. So we write I mu is equal to V pi divided by 1 by j omega C naught, because it's not the current flowing through C pi, sorry, the current flowing through C mu, which will actually flow through C pi when you replace C mu with a certain equivalent capacitance. And we want the current to remain the same, right? So the current flowing through this equivalent capacitance should be equal to this particular current, which we found out to be j omega into C mu into 1 plus gm RL dash into V pi. So the current across C equivalent should have to remain the current across C mu. So we will have to take the value of the capacitance such that the current flow remains same. So we have V pi into C omega, C equivalent into J omega is equal to J omega into C mu into 1 plus Gm RL dash. So my J omegas get cancelled and my V pi's also get cancelled. The only thing I'm left with is C equivalent is equal to C mu into 1 plus Gm RL dash. So now we have simplified this circuit a lot. We just have one resistance here, one capacitance, one voltage source here, a dependent current source here, and one resistance here. So this is how we have gone from a complicated circuit like this to a circuit which is as simple as this, where this is RL dash, this is my R signal dash, this is my capacity input, and this is my V signal dash. So C input is just where your C pi is parallel with C equivalent, that is C pi plus C equivalent. So the simplification of the capacitances that we tried to find by taking the current flowing through both of them to be the same, that can be done in a much simpler way using this theorem known as Miller's theorem, which is used to simplify circuits. So what Miller's theorem says is, if you have an impedance Z across two different potentials V1 and V2, this can be replaced with two different impedances connecting each of the potentials to the ground. This is Z1 and this is Z2, where Z is equal to 1 minus K, Z1 is equal to Z divided by 1 minus K, and Z2 is equal to K into Z divided by K minus 1, where K is the voltage, the potential, uh, the the division of the potentials present across each terminal. So K is V2 divided by V1. So how I express my impedance as a form of K is the current flowing through this impedance, which is I1. Let's say it's given, it flows from V1 to V2. So I write it as V1 minus V2 divided by Z, the potential difference divided by the impedance. So upon taking V1 common from this, I have 1 minus V2 divided by V1. And V2 by V1 is K. So I can write I1 as V1 into K divided by Z. So I1 by V1 is equal to Z1, which is equal to 1 minus V1 into 1 minus K. Yeah, 1 minus K divided by Z. So no, I1 by V1 is equal to 1 by K by Z, and Z1, which is equal to V1 by I1, is equal to Z divided by 1 minus K. So this is the derivation for Z1, and for Z2 we assume it to be the other way, that is V2 minus V1 divided by Z. This was V2 and this is V1. So V2 minus V1 divided by Z. So upon taking V2 common here, I get V1 by V2, and K was V2 by V1. So this becomes 1 by K, and upon simplifying this, I get Z2 is equal to K into Z divided by K minus 1. So similarly, by looking at these two terminals, my the in V1 the V1 that we assumed so far would be in this case V pi, and V2 in this case would be the output voltage. So we have K, and so we just need to find Z, and Z would just become Z1 would be Z divided by 1 minus K. So what is my total impedance here? The C input, which is no, the C equivalent, which will be denote the impedance for which will be denoted by J omega C input divided by 1 minus K. So I get 1 by J omega C input into 1 minus K. And upon replacing K with VO by V omega, we get the same expression for equivalent capacitance that we got last time. So okay, so now we need to find the voltage gain, right? Which was supposed to be VO divided by V signal, right? So to find VO by V signal, we already found a relation of the V output with V pi. So like I said at that time, we need to find a relation of V signal with V pi 2 so that we can directly relate both of them. So you can see that V pi can be found, the relation between V pi and V signal dash can be found using voltage divider rule. So upon applying that, we get V pi is equal to V signal dash, which is my source voltage, into the impedance across V pi, I mean across C pi, divided by R signal dash plus the impedance across this capacitor. So I can write this as 1 divided by SC input, and upon adding and taking the LCM, I get SC input in the denominator too, and they cancel each other out. So what I'm left with is V signal dash into 1 plus S into R signal dash into C input. So our main aim in these circuits, that is low frequency and high frequency, will be to get the circuit in this type of form. It's always to get it in the form 1 plus 1 divided by 1 plus something, or 1 s divided by s plus something. So this thing that we have here, this is what we'll call, this is what is 1 by omega. And so I replace R signal dash into C input with 1 by omega naught. So omega naught is the angular frequency at the corner. So anything higher than this frequency, your gain starts to fall. In the, like we saw in the Bode plot, the gain starts to fall after a certain frequency. That frequency is called omega naught, and this is the angular frequency. The actual frequency f naught is given by 1 by 2 pi into R signal dash into C input. So this is called the corner frequency of a STC. STC stands for single time constant network. We'll learn more about single time constant in when it comes to low frequency analysis. So now the thing that what we need to find is we need to find our voltage gain. So to find voltage gain, we have V pi in terms of V signal dash, and we also have V pi in terms of VO. So VO by V pi was GM by RL dash minus GM by RL dash, like we have, like we solved it here. So we express VO by V pi with minus GM RL dash, and we replace V pi by V signal dash with 1 divided by 1 plus S by omega naught. And we also know that V signal dash was not our original input voltage. That was taken by reducing the overall circuit with Thevenin's theorem. So to find the whole thing out in terms of our initial V signal, we take V signal dash divided by V signal. So we know that we know what V signal dash was in relation to V signal. So we replace it with all those terms, R pi divided by R pi plus Rx plus R signal parallel to RB. We take all of the terms out except this particular term. So this bracket that you have here is called the midband gain. So this is the, on the Bode plot, there was a certain region here. This part, the height here was 20 AM. So the AM here is what midband gain is. So to find out the voltage gain for the midband, you just have to multiply it with 20. And this midband gain is the region where your voltage amplification is optimal because no capacitances are in effect, and it lets the voltage amplification take place smoothly. So I finally get the voltage gain as AM divided by 1 plus S by omega naught. So like I said, my frequency F naught is 1 by 2 pi into omega naught. No, it's omega naught by 2 pi, and it's 1 by 2 pi R signal dash into C input. And again, I know the value of C input to be C pi plus C mu into 1 plus GM RL dash. So this particular gain that I have is of a low pass type due to the presence of these capacitances. So what is a low pass filter? A low pass filter is when higher frequencies are allowed to pass through. No, a low pass filter is when lower frequencies are allowed to pass through and higher frequencies are just obstructed. So how do we actually find out whether a given circuit is high pass or low pass? We have a look at the the gain, which is VO by V signal, and in this case we have VO by V signal in terms of we have it in terms of this particular thing, which is 1 divided by 2 pi. No, this is not what we should be looking at. I'm very sorry for this. Just a second. Okay, so when we are looking at it from the input side alone, we have V signal dash, we have R signal dash, and we have C input, which was calculated as the resultant of the C equivalent and C pi being in parallel. So there is a certain voltage VO, let's say across the capacitance, or let me take it as V dash. So my V dash is equal to V signal dash into 1 by j omega C input divided by 1 by j omega C input plus R signal dash. So upon solving this, uh, let's take we get V signal dash into 1 divided by R signal dash plus j omega C input. Okay, so this is our final expression. So what we need to look at here is we need to see what type of filters, what type of frequencies are actually allowed to pass through in this case. So first let us check with low frequencies. Now if I take omega is equal to 0, no. This will be 1 plus R signal dash into j omega c n. So yeah, if I take omega is equal to 0, the entire part over here becomes 0. So my voltage gain tends to be 1. So if I'm getting voltage gain out, that means there is some sort of output. So low frequency signals are allowed to pass. To check for high frequencies, let me take omega is equal to infinity. So upon substituting omega as infinity, my denominator becomes infinity and 1 by infinity is 0. So basically, there is no output. So that means that the higher your frequency goes, the lesser and lesser your voltage gain becomes. And at one point, the the frequency will not even be allowed to pass through. Like you can see at omega is equal to infinity, or the output becomes 0. So that's the issue here, is that at high frequencies, because of your capacitors, the entire circuit tends to act as a low pass filter. And what a low pass filter does is it does not allow high frequencies. So because of that, after a particular frequency, due to the effect of these capacitors, your circuit behaves like a low pass filter and the voltage gain falls off. So that is the reason for this fall off here. This is the this is the frequency that we calculated with omega naught. This is F naught. So after F naught, the entire thing, your voltage gain reduces, and there is always a 3 decibel gap between mid-band gain and the point where the graph falls off. This is present on both sides of this curve, on the high frequency side and on the low frequency side. So we know that our frequency, this particular frequency is given by 2 pi into Cn into R signal dash. And we also know what R signal dash is. We know what we have simplified to get R signal dash, and we also know what we have simplified to get C input. So that is our high frequency analysis. So what we have learned in high frequency analysis is that at higher frequencies, your voltage gain falls off because of certain capacitors, the parasitic capacitances, C pi and C mu. What these capacitors do is they make the circuit act as a low pass filter. So because of which the higher and higher your frequencies get, the lower and lower your voltage gain goes until it finally becomes zero. So we have simplified this circuit and gotten a simple circuit. This simple circuit is what we've gotten, and through this simple circuit we've gotten the relations between input, output, and the voltage gain. And we have also learned that there is a simpler way to reduce our circuits, which is Miller's theorem. That is about high frequency analysis. Now let's look at low frequency analysis. So in low frequency analysis, we take the same circuit as high frequency analysis, but the additional resistances RO and the Rx that was here in parallel, uh, in case no, sorry, RO and this is Rx. The Rx and RO that we had earlier and the RB, they're all going to be omitted because those those resistors always are taken in values which are in tens of ohms. So because of which they are negligible at low frequencies. The other resistors you have here, they are usually in terms of kilo ohms, due to which they are still prevalent at this frequency. So when it comes to low frequency response, the C pi and C mu, they don't have any use, they are just short circuited. But your CC1, CC2, and CE, these are the capacitors which actually affect our circuit at low frequencies. So while looking for low frequencies response, what we do is we cannot take all three of them and calculate the response at once because each of them are connected to different terminals. So we take one at a time. We calculate the omega naught due to each capacitor, and then in the end we plot all of them together at the on the board plot. So the first thing is we'll take only CC1. So CC1 is the capacitor before, right beside our base terminal. So this is our circuit when we are taking CC1. So let's start with R pi, the resistance R pi. So we find the potential difference across that using voltage divider rule. So V pi can be written as V signal into what is the impedance here, which is RB parallel to R pi divided by RB parallel to R pi and plus R signal plus 1 divided by SCC1. So this is the total impedance, and this is the impedance across the region that we are trying to actually find the potential. And we can see that the output voltage will be the current flowing through the equivalent resistance of these two. And we can see that the current flowing here is G pi into Gm into V pi. So since we are taking the opposite direction, my V output will be minus Gm into V pi into RC parallel RL. So here I have my V signal in relation with V pi, and here I have my V output in relation with V pi. So I take VO by V signal is equal to output by V pi into V pi divided by V signal. So we just saw that output divided by the potential difference across R pi will give us minus Gm into RC parallel to RL. And we also derived the expression for V pi we also derived the expression for how our input signal is related to the potential difference across R pi. So we write these two, and like I said, we try to get an expression of the form S divided by S plus 1 by something. So that's what we'll be working towards here. So now that we have this, we try and simplify our expression to get to this point. So we take RB parallel R pi out of the bracket, and we are left with 1 divided by parallel to R pi plus R signal. So since we want something of this form, what we do is we take this term common outside the bracket, and we write RB parallel to R pi plus R signal plus 1 divided by SCC1. So out of this we take RB parallel to R pi plus R signal common, and I'm left with 1 plus 1 divided by SCC1 into RB parallel to R pi plus R signal. Right? So now I can take this part outside. So this part also comes here after taking it common. So I'm left with 1 plus 1 by S CC1. So again I take 1 by S common out of this. So and then the 1 by S in the denominator goes and becomes S in the numerator. So I get my expression of this form. So my STC of this particular capacitor comes out to be 1 divided by CC1 into RB parallel to R pi plus R signal. So this resistance, which is RB parallel to R pi plus R signal, this is basically, let's call it R1 for now. This is the resistance that is actually seen from across the terminals of the capacitor. So we label this as omega P1 and FP1 because we are taking three different cases. So we get omega P2 and FP3 later on. And all of them will be plotted on the board plot, and they're all different places where the graph tips. So, like you can see here, the this says that this is a filter of high pass type. So what actually happens here is you have something of the type 1 divided by C C1 into, let's, since we took it as R1, we have it of the type CC1 plus R1. So the total resistance that is actually going to be here will be given by 1 divided by, we'll actually just do this part later on because we'll need to know all three capacitances for this. So for now, you just need to understand that we've obtained, you just need to understand how we obtained the value of omega P1 for the first capacitor alone. So next what we do is we take another capacitor which is CE. So here we write this resistor as Re into beta plus 1 because that is what R pi was equal to, and we write CE into beta plus 1 here because of the resistance reflection rule that we learned. The emitter capacitance is actually supposed to be on the emitter terminal, but since we are taking all our devices on the base terminal, we are going to take our capacitance here and replace it with a capacitor of the value C into B plus 1. So now what we do is we try to simplify the input part of the circuit and we do it using Thevenin's theorem. So we can replace V signal with V signal into RB divided by RB plus R signal because that is the potential difference across RB using voltage divider. So we replace V signal with VTH, and then we have that R signal is parallel with RB. So we can replace this part with just one voltage source and one resistor. So now that I have one voltage source, two resistors and one capacitor, I can write IB, which is my base current, is equal to the potential divided by the total impedance here. And the total impedance here is RTH plus RE into beta plus 1 plus XCE into beta plus 1. We know VTH is equal to V signal into RB divided by RB plus R signal, and we can also write XCE as 1 divided by SCE. So what we are actually trying to find here is the relation. We are going to relate VO and V signal using IB. In the previous case, we used V pi as a common term to relate both of them, and now we'll be using IB. So we know that the output voltage is equal to the current flowing through the equivalent resistance between these two. So the equivalent resistance between these two is RC parallel to RL, and the current flowing through them is minus GM V pi or minus beta IB. Since we are trying to solve it through IB, we are going to take IB here, and so after taking that, we are going to write IBS using IB using our input signal. So we learned that IB is equal to this expression, this huge expression. So we're just going to replace IB with that expression. So now again we do the same thing where we take each term out one by one and until we are left with 1 plus beta plus 1 divided by cc1 into rb parallel to r signal plus beta plus 1 into re. So like you must have noticed by now, it's the same pattern in everything where you just have to find the input voltage in relation with V pi or IB and find the output voltage in relation to them as well and try to get it to the form of 1 divided by 1 plus something or s divided by s plus something. So I am stressing on that because derivations are an important part in the exam. So instead of actually cramming every single derivation which is there, it's actually not that hard to just get the flow of every single one of them once you actually understand it. So I hope by now everyone's understood the first few derivations, and so because of that the following ones just become easier. So this equivalent resistance that I have can be denoted with R2, and the entire uh, what do you say, the entire frequency is denoted with omega p2. So that is now we've seen it in terms of CE. So the last one is CC2 alone. So CC2 is between the collector and the load. So now again what we do is we find V pi using voltage divider. We found V pi, and now we are going to find VO in terms of V pi. So what is VO? The current that is flowing through the equivalent resistance of these two. So now the only issue with this, which we did not face with CC1, is the capacitor which is coming here. So what we do is we apply current division rule to find out how much current goes through RC and how much current goes through IL. So once we find the current that goes through RL, we can find out VO as IL into RL. So we know that our GM V pi is splitting into IC and IL. So how much flows through RC and how much flows through this capacitor and RL is found using current division rule. So in current division rule, what we do is we take, if we are if current is splitting in parallel between two devices and we are trying to find the current across this, we take the resistance of the other value in the numerator and the sum in the denominator. So here we are trying to find the value of current flowing through uh, CC2 and RL. So we take RC divided by RC plus RL plus 1 by SCC2. So upon doing that, we got IL. So V naught is going to be RL into this entire expression. So we got V naught, and we know that V pi can be expressed using V signal. So we replace V pi with that, and then what we do is we take V signal to the other side so that we can get the voltage gain V output in the numerator and V input, which is V signal, in the denominator. So again, I just simplify this particular expression to get S divided by S plus 1 by CC2 into RC plus RL. So this RC plus RL is my R3, and this entire thing is this entire term is denoted with omega P3. So now I have found all three angular frequencies. So before we actually plot them on a board plot, let's actually let's actually learn this method, which is actually much easier and helps us find our angular frequencies really fast. So while I was writing R3, R2, and R1, I said that they are the resistances when seen through the terminals of the capacitor. So what we do is we actually just open the terminals of every capacitor one by one and see what is the resistance across each of them. So this is called the time constant technique. So here what we do is we short circuit our source voltage, we short circuit all voltage sources, we open circuit all current sources, and other capacitances are short circuited. So first let's talk about CC2. That means CC1, CE, and every has been they have been short circuited, and the sources also have been short or open circuited. So now when I open the terminals of the capacitor, what I have is my RB is in parallel with RPi, and the resultant resistance between them is in series with R signal. So because of that, what I have is the R equivalent. So we all know that tau or time period is equal to R into C. So I find tau by multiplying the equivalent resistance with the capacitance which was present, which is CC1. And we also know that F is equal to 1 by 2 pi into tau. So whatever RC we get here, uh, your F just becomes 1 divided by 2 pi into RC. So R is R equivalent and C is CC1. So, and we know that R equivalent is RB parallel to R pi plus R signal. So now let's just see here. Right. So this is the same expression as we got in using this extremely lengthy method, but we got it here in just a single step. So this step helps us find our frequencies in just 2 to 3 steps for lower frequency, lower frequencies. Uh, and to find the actual voltage gain, you will have to uh, multiply it with k into s divided by s plus omega. The value of k is fixed, and you'll have to remember that if you are using this method to derive lower frequency values. So now that we found it with CC1, when we do the same thing with CC2, we have RC and RL both in series. So that becomes my equivalent resistance. Uh, so I find tau with RC plus RL into CC2, and again my frequency is just 1 divided by 2 pi into time period. So for CE, what I have is my R signal is in parallel with RB, and that the resultant of them is in series with RE into beta plus 1. So again, that this is a very simple technique which allows me to derive the expression for frequency in just 2 steps. So the most important thing that you need to remember here is FP2 is always the first. It's it's much higher than FP1 and FP3. So FP2 is the frequency due to your emitter capacitance. So the usual value of FL is the place where it starts going down. That is 3 decibel below your midband gain region. So FL is equal to FP2, and usually FP3 is equal to FP1 is equal to 10% of FL. So this is the usual these are the usual values of these frequencies. So unless if the values are not specified in the question, this is you can take these as the values where FL is equal to FP2 and FP3 and FP1 are just 10% of FL. Okay, so with that we have come to an end of low frequency analysis. So we just have one topic left, which is multi-stage amplifiers. After which we'll see a few questions about uh, what do you call them, AC biasing, because we have already done the required questions for DC biasing. So we'll solve 2 3 questions, one on high frequency and one on low frequency, and that will be it for the chapter. So before that, we'll talk about the small theoretical topic, which is multi-stage amplifiers. So what multi-stage amplifiers do is they help us in getting better amplification. So we use 2 or more amplifiers. So the input is sent into the first stage amplifier and you get a certain amplified output. To further amplify this output, what we do is we send it into another transistor again, which is called the second stage transistor. So an already amplified output is getting amplified again, due to which you are getting a much more amplified output. So to get higher amplification, we use multi-stage amplifiers. So there are multiple types. So if we are using 2 or more common emitter amplifiers itself, it's called a cascaded amplifier. And if we have a common emitter in the first stage and a common base in the second stage, it's called a cascoded amplifier. So first, what we will talk about is cascading amplifier. So in cascading amplifier, there is always some coupling in between the different when you have 2 different amplifiers, between them you have something to couple both of the circuits together. So this is done. Cascading amplifying is done when you want to send the AC output of one stage to the input of the other amplifier, the other transistor. So the DC part is isolated and the AC output is what is being sent. So since coupling is essential, it can be done in 3 different ways. One is capacitive, the other one is directly connecting it, and the third one is transformer. So this is the first type, which is capacitive coupling. So like you can see, this is a normal amplifier in voltage divider bias. And again, if you look at it from this, just look at this alone, you have another amplifier in voltage divider bias. But these two are joined, you just have one source voltage, and these two are coupled with a capacitor. So you if you view the circuit individually, they both are 2 different circuits having voltage divider bias, but they are coupled together with the help of this capacitor. So this is capacitive coupling. Direct coupling is when you apply 2 different voltages to each part of the circuit and you directly join the input to the output without the capacitor to couple each of them. So because of this, you are forced to put another source voltage to the second stage of this amplifier. And the last one is transformer. So we know that transformers can already be used for amplification using the number of turns on one side. So if you have N1 turns on this side and N2 turns on this side, your V1 voltage gets amplified to V2, where your N2 by N1 is equal to V2 by V1. So this is transformers can already be used for amplification, and in addition to that, they are also used to couple these two transistors. So like you can see, there is just one source voltage here. There is a transformer to help us in coupling, and there is an output transformer to help us in amplification even more. So this is the most ideal coupling scenario because it helps us in getting maximum amplification. So this is the cascading amplifier. So cascading amplifiers are used for voltage amplification primarily, and they are the best for voltage amplification. So let's say if you use one of these amplifiers individually, you get gain of X, and if you use the second one individually, you get a gain of Y. So upon cascading both of them, the overall voltage amplification you get will be a product of X and Y. So this cascading is perfect when you are trying to get voltage amplification. The second one is cascoded. So that is where you have a, this is my first stage. So in my first stage, I have a common emitter, and in the second stage, I have a common base. So here, what happens is there isn't much voltage amplification. It's not really the ideal one for voltage amplification, but we have a very high input impedance. Because of these, because of the high input impedance, what happens is the capacitances, the parasitic capacitances, they their effect drastically reduces. So what happens is even if you have a high frequency, this sort of gets the job done, even though it's not perfect amplification for every frequency. When it comes to higher frequencies, this is ideal because uh, this configuration manages to negate the effect of other capacitors. So, and the last type of connection that we have is the Darlington connection, which is the best for current gain. So, this type of a connection, what happens is, let's say individually each of these transistors have a current gain of beta 1 and beta 2. Now they're going to have a current gain which is equivalent to the product of their individual gains. And when you attach these two uh, transistors in a Darlington connection, they always act as if they are a single unit. So with that, we are done with multistage amplifiers too. So let's just solve two questions on high frequency, one on high frequency analysis and one on low frequency analysis. And we will be done with this chapter. So the first, so just have a look at the formulae and solve them. So the first question says find the midband gain. We are supposed to find midband gain, and it's given that it's high frequency, and we are given VCC is equal to 10 volt, IC is equal to 1 milliampere, RB is equal to 100 kilo ohms, RC is equal to 8 kilo ohms, R signal is equal to 5 kilo ohms, beta naught is equal to 100, and okay, and I'm given C mu. C mu is equal to 1 picofarad. Ft is equal to 800 megahertz, and Rx is equal to 50 ohm. So we are supposed to find the midband gain and the upper end of 3 decibel frequency. So what this means is when you have the Bode plot, your graph goes something like this, and this is your 3 decibel line. You're supposed to find the midband gain as well as this 3 decibel line at the upper end using the given data. So the first thing that we'll do is we can find our midband gain AM with the formula minus RB divided by RB plus R signal into R pi divided by R pi plus Rx plus RB parallel to R signal, and this is multiplied with GM RL dash, and we know that RL dash is equal to RO parallel to RC parallel to RL. So we have what do we have here? We have only RC. So let's not try and find that. We have GM and okay, we have IC, right? So we know that GM is equal to IC divided by DT. So we can write that as 1 divided by 26, which gives me approximately 0.04 Siemens. So now that we found GM, we know that GM GM by beta naught. No, we know that beta naught is equal to GM into R pi. So now we know beta naught, we know GM. So let's find R pi. R pi will be beta naught divided by GM, which gives us 100 divided by 0.04, 2.5 kilo ohms. So next what I do is and we are also given another information, which is VA is equal to 100 volts. So we also know that RO, this is the output resistance, is always given by VA divided by IC. I think this is a new formula, so this wasn't used in any concept while explaining the actual models. But yes, this is handy in question. So this is another formula which has to be remembered. So we have R naught. We know VA is 100. We know IC is 1 into 10 to the power minus 3. So we have 100 kilo ohms again. Next we have RB parallel to R signal. So we know RB is equal to 100 kilo ohm and R signal is 5 kilo ohm. So that gives us 100 into 5 divided by 105 is equal to 4.76 kilo ohm. So now we've gotten all the values necessary. We have RB, we have all of these. Okay, so now we can finally write the values and find our midband gain. So I have AM is equal to minus 100 divided by 105 into 10 to the power. No, this wouldn't be necessary then. Into 2.5 into 10 to the power 3 into 0.04 into 2.985 into 10 to the power 3 divided by 2.5 into 10 to the power 3 plus 50 plus 4.76 into 10 to the power 3. So that leaves me with minus, upon solving all of this, you get minus 38.94 approximately. So we know that the actual upper end is, we know that the proper midband gain is given by 20, no, not, why am I writing log? Okay, so we know that the actual midband gain is given by 20 log mod of AM. So that means 20 into log of 38.94. This gives us 32 decibels. So now this we have our midband gain. We have done half of the question. So the other half of the question asks for the other half of the question asks for the frequency at which the upper 3 decibel frequency, which is the frequency at which uh, the voltage gain goes down. So for that we have FH is equal to 1 divided by 2 pi R signal dash into C input. R signal dash is equal to R pi parallel to Rx plus RB parallel to R signal. So we know we found R pi to be 2.5 into 10 to the power 3, and this is in parallel with Rx, which is 50, and RB in parallel with R signal. Did we solve that somewhere? Yes, that is 4.76 into 10 to the power 3. So the final answer that we have here is 1.645 kilo ohms. So that gives me R signal dash. Now I have now to calculate C input. C input is C pi plus C mu into 1 plus GMRL dash. Okay. So with that, okay, I also know FT is equal to GM divided by 2 pi into C pi plus C mu. So my C pi plus C mu actually gives me Gm divided by 2 pi Ft. So I know C pi is equal to Gm divided by 2 pi Ft minus C mu. I know the value of Gm is 0.04, 2 into 3.14 into. It's given that I am given that uh, Ft is equal to 800 megahertz. So I can use that here, 800 into 10 to the power 6 minus 1 into 10 to the power minus 12. Okay, so from that I get C pi is equal to 6.96 picofarad. So now I have to find C input by 6.96 plus what is C mu? C mu is 1 picofarad. So this becomes plus 1 into 1 plus 0.04 into 2.985 into 10 to the power 3. That gives my C input as 127.36 picofarad. So now I have both my capacitors. I just need to substitute it in FH, and I have 1 divided by 2 into 3.14 into 1.645 into 10 to the power 3 into 127.36 into 10 to the power minus 12. So finally I get my answer as Fh is equal to 760 kilohertz. Okay, so the only real issue with it is the really exhausting and daunting amount of formulae that have to be applied. But trust me, once you have actually gone through the concepts and understood how each formula has come, after I, it's understandable if you are not solving the question right now. The purpose is not to get it solved as of now. I'm just solving these two questions to show how any question in general is supposed to be approached when it comes to a high or low frequency analysis. But it's essential that you remember all the formula and everything is on your fingertips so that you understand that you can get the information they're asking with whatever information is given. So it's this question is just to show how the flow of solving a question goes and how you just approach a problem in general. So let's just have a look at another question in the lower frequency in low frequency analysis. So they're asking us to find CC1, CC2, and CE when RB is equal to 200 kilo ohms, RC is equal to 5 kilo ohms, RL is equal to 10 kilo ohm, R signal is equal to 5 kilo ohm, beta naught is equal to 50, RE is equal to 19.6 ohm, R pi is equal to 2.5 kilo ohm, and FL is equal to 200 hertz. So now we have FL. So we know that FL is equal to FP2, which is 200 hertz. So we take FP1 is equal to FP3 is equal to 10% of 200, which is 20 hertz. So now we know the FPs, we know the frequencies, we know the break frequencies, and we need to find the capacitances. So we know that the relation is the frequency is equal to 1 divided by 2 pi into capacitance into resistance. So what we need to find is the equivalent resistances R1, R2, R3, and we'll be done. We can find each capacitance. So for RC1, I know the formula is R signal plus RB parallel to R pi. So that gives me 5 kilo ohm plus 200 kilo ohm. And this is in parallel with 2.5 kilo ohm again. So my final answer comes out to be around 7.47 kilo ohm. Right, so now I found RC2. I can find FP1. I know it's equal to 20. 20 is equal to 1 divided by 2 into 3.14 into CC1 into 7.47 into 10 to the power what was RC1? 10 to the power 3. Right, okay, so upon multiplying this, I take CC1 to the other side, get CC1 is equal to 1 divided by 2 into 3.14 into 20 into 7.47 into 10 to the power 3. So this comes out to be 1.07 into 10 to the power minus 9 farads, which is around 1 point, which is 1.07 microfarad. This is minus 6. Man, the amount of silly mistakes. Okay, so that is CC1. So now for uh, RC2, I know it's RC plus RL, which is wait, this is yeah RC2. RC2 is RC plus RL, which is 5 into 10 to the power 3 plus 10 into 10 to the power 3, which is 15 into 10 to the power 3 ohm. And so while solving FP2 again, it's 20, and this is 1 divided by 2 into 3.14 into 15 into 10 to the power 3 into CC2. So upon taking CC2 here and 20 here, I will get CC2 is equal to 0.53 microfarad. And the last one, RCE, is equal to small re plus RB parallel to R signal divided by beta plus 1. So I am given that RE is 19.16. This is 200 kilo ohm. This is 5 kilo ohm. 50 plus 1. So that gives me 19.6 plus 200 into 5 divided by 205 into 51 into 10 to the power 3. So that is around 115.25 ohms. So now that I have the resistance, the capacitance is just a step away, which is 2 into 3.14 into, what was the value? 115.25. So I find out that my CE is around 6.9 microfarad. So yes, 6.9. That ends it on a good note. So that's the end of the chapter. That's that's the end of this module. I know the amount of formulae is exhausting and it might take some time to just remember all of them, but I hope watching this video at least made you understand and made it a little easier to get a hang of how the derivations are done and how the concept behind simplification of these circuits work. Because once that is understood, deriving the formula is not really a big deal. Because as you must have noticed, almost all of them have very similar similar derivations. So that is not really a hard thing when you look at it. But yes, you will have to spend at least an hour after this, just memorizing all the formulae if possible. Like if there is time, of course, just write everything. But if not, just memorizing the formula and going through a few questions, few solved examples should get the job done. And if you found the subject actually interesting and wanted to learn more in depth about certain points, but we couldn't because it wasn't what this module required, then you don't have to worry because there are many upcoming videos where we'll cover each and every single topic in detail. And I'm sure every single minor aspect of this, like two-port networks, BJT, the different modes of BJT, how the capacitances are actually formed. Everything will be explained in different modules. But for now, I hope you found this interesting. I hope this gave you some interest towards the subject. I hope it made your approach towards the subject a little different. I hope it will fetch you certain marks in the subject. Thank you for listening, and I hope it was helpful.